Hello everybody. Module 14, Kinetics. You can find this module on page 459 in your textbook. So we're going to cover all the way to example 14.4. The module covers the following. Reaction kinetics. What is that? Well, you're going to be learning about it. Factors that affect the kinetics of a chemical reaction. The rate equation. Using experiments to determine the details of the rate equation. Rate order, using rate equations, catalysts, and reaction rates. So lots of information, but we're going to tackle one at a time. So in the previous module, we learned about thermodynamics. We learned about Gibbs free energy, enthalpy, and entropy. And how a reaction to be spontaneous needed a Gibbs free energy that was smaller than zero, so it was negative. Gibbs free energy, enthalpy, and entropy are thermodynamic criteria. But that's not the only criteria that will decide if a chemical reaction is really spontaneous or not. Some reactions are spontaneous, so their thermodynamic criteria is good. They have a Gibbs free energy that's negative, but they take a long time to happen. It could take years for that reaction to happen. So chemically speaking, that reaction is not usable. So here you go. Thermodynamic criteria, meaning Gibbs free energy, enthalpy, and entropy, is not the only factor influencing how practical the chemical reaction is, because some of them can take years to proceed, and that for us is not good if we want to create whatever product we want to create. So we also need to look, besides thermodynamic criteria, we also need to look at the chemical kinetics. What is that? Kinetics means speed, the rate of that reaction. We need to study how fast that reaction is. So when we study chemical kinetics, we're studying the speed with which a chemical reaction occurs and the factors that affect that speed. We can speed a reaction by changing a few things. We're going to learn about what can we change to speed that reaction or to slow down that reaction if that's what we want to do. Chemical kinetics also provides information about the feasibility of the chemical reaction. If it's going to take 100 years for that chemical reaction to happen, it's not any good to us. We're not going to be around by the time it finishes. Chemical kinetics also provides information about the time it takes for a chemical reaction to occur. Provides information about the series of elementary steps which lead to the formation of product. So all of these are covered under kinetics. Now, let's define what reaction rate is. Page 459 plus in your textbook. So you need to be able to define kinetics and reaction rate. The rate of a chemical reaction is generally measured in terms of how much the concentration of a reactant decreases in a given period of time. The reactants disappear while you're producing product, and then you start seeing how product appears. It looks like it's appearing. Okay? So we can look and see how that reactant is decreasing, or we can also look at how the product concentration is increasing. The same, two sides of the same coin. So here we go. Rate is the change of the concentration over time. How does that concentration changes? And we can look at it from the product side or from the reactant side. The product is being produced, so we're giving it a positive sign, is increasing. And if we're looking at it from the reactant side, what's going on, it seems to be disappearing. it's decreasing the amount of reactant. The units are going to be in molarity per second. Those are going to be our units when we do problems with rate. You are going to be performing experiment 14.1 on page 460 plus in your textbook. So you're going to be studying factors that affect chemical reaction rates. And we're going to talk about your results in more detail during our Zoom meeting. Let's look at them one at a time. Reaction rate factors. So what affects the rate, how fast that reaction is going? The nature of the reactants, the concentration of those reactants, the surface area of those reactants, if you add or not a catalyst, and we're going to see what that is, and increasing the temperature. So let's look at it one at a time. In order to react, chemicals must collide with one another so that their electrons can either be transferred or rearranged. This is on page 462 in your textbook, and this should make sense to you. You already know about some reactions between metals and non-metals. One takes, the other one gives away those electrons. If you have non-metals, they're going to be sharing. So it's all about those electrons. And for that to happen, those atoms need to be close together. They need to collide. That's the first step. They need to come in contact for those electrons to move. We can increase collision between atoms and molecules if we increase the temperature. So higher temperature increases chemical reaction rates because the reactant molecules or atoms move faster, increasing the chances for collisions between them. So here you go. They were moving around, you increase the temperature, what happens? They're moving faster. As they move faster, they collide with one another more often. And that allows them to exchange electrons or transfer electrons. If this does make sense, please ask questions. Now, let's talk about concentration. Decreasing concentration decreases the chemical reaction rate because there are fewer molecules or atoms to collide with one another. So this is always true. If you decrease the concentration, you decrease the rate. The opposite is not always true. So increasing the concentration not always increases the rate. Decreasing always decreases. Okay? So here you go. Lower concentration, higher concentration. Now, increasing the concentration not always increases the rate of a reaction. When that happens, we say that the rate is independent of the concentration for that reactant. So here you have a concentration of a reactant A over time, and here's the rate. So how fast is that reaction going? And as you see, it's a flat line. Means it doesn't matter if you're increasing the concentration of that reactant. It's not affecting the rate. Decreasing always decreases, but increasing not always increases the rate. And you need to know that. Now, another thing that affects the rate of reaction is the surface area of the reactant. Increasing the surface area of a reactant increases reaction rates because the molecules or atoms of the reactant can more easily mingle with the atoms or molecules of the other reactant. So here you go. You have a big piece of reactant A. Reactant B is coming and colliding with the surface area of reactant A. There's only a certain amount of collisions allowed when you have this kind of surface area. If you break apart, increasing the surface area, reactant A, here you go, other chunks, smaller chunks, you're increasing the surface area of that reactant A. There's more surface area for reactant B to collide with it, increasing the rate. Okay, let's talk about catalysts. That's another thing you can use to increase the rate of reaction. A catalyst is a substance that you, a chemist, puts in the reaction to speed up the reaction without actually getting used up in the chemical reaction. And we're going to be studying catalysts in kind of in more depth in the future. But for right now, you need to know that. This is on page 480. So here you have an exothermic reaction. See, the reactants are up here, the products are lower, so this is exothermic. We already know about activation energy. And here we have the activation energy without the catalyst. So you need a lot more activation energy. And here's the activation energy with the catalyst. So catalysts work by lowering the activation energy needed to start that reaction. So that reaction can proceed faster. And they don't get used up. Page 464 in your textbook. The rate equation. We can determine exactly how much the reaction rate changes when reactant concentrations change. For example, given this generic chemical equation, so we have reactant A and B to give product C and D. This equation allows us to find the rate of this reaction. The rate equals K is a constant and is unique for each reaction. The units of K change depending on the order of the reactants, and you'll see what the order of the reactants means. Brackets mean concentration, so we have concentration of reactant A, concentration of reactant B. X and Y, right here, are the order of the reaction with respect to each reactant. X is going to be a number, Y is going to be a number. So that number is the order of the reaction in respect to reactant A, and Y, whatever number that is the order of the reaction with respect to the reactant B. And X and Y, those numbers, those values, can only be determined by experimentation. X and Y have nothing to do with the little letters here, with the stoichiometric numbers, okay? Are determined by experimentation. When you add X and Y, you will get the overall order of the reaction. And they will ask you that, okay? Sometimes they'll say, what is the overall order of the reaction? And to find that, you just add the value of X plus the value of Y. If they say, what is the order of the reaction with respect to reactant water? Then you would read X, the number in X. What is the order of the reaction with respect to whatever this reactant B is, ammonia? Then you would read whatever exponent you have in Y. That's how you read the rate equation. Now, page 474, moving on. The reaction rate order for a chemical reaction must be determined by experimentation. They are not equal to the stoichiometric coefficients in the chemical equation. It's very, very important for you not to get confused. You have to calculate them. And you're not going to be doing a lot of experiments. You're going to be analyzing data from experiments in this module. Let's look at example 14.1 on page 465 in your textbook. Write the rate equation for the following chemical reaction. So you have nitrogen and hydrogen to give you ammonia. So what is the rate equation? They're going to ask you questions like this. Let's go to the board right here and let's see how this is done. Okay, let me write down. Let me get on my mouse. the I'm copying these 3H2 ammonium 2NH3. Okay, remember that the rate equals K, concentration of reactant A to the X, times concentration of reactant B to the Y. So what can we put in here? Well, the rate is going to be a constant. Do we have any constants here? No, we have no idea. They didn't give us any information. What is A? A is a nitrogen. So whatever the concentration of nitrogen is, that is going to go in there. X and Y are not the stoichiometric coefficients. They're not the 1, the 3, or the 2. They are determined by experimentation. They didn't give us the information. We'll leave it alone. What is B? Is the second reactant. In this case, is hydrogen. And Y was not given to us. So we're going to leave it like this. That's all we needed to do. We're going to do extra practice problems 1 and 2. I think this is what it said in there. Let me check. Maybe not yet. Just let me see. Yes, we should be doing extra practice problems 1 and 2. I didn't write it here, but we do need to do it. Well, we don't need to, but it's good to do it so we can practice before you have to do it on your own. So you're going to find them on page 582 in your textbook. Number 1 reads as follows, and both of them are thinking problems. With the information that you have, you need to reason through what they're asking to see if you can solve them. Number 1 says, a chemistry book lists the rate constant for a reaction as 34.51 divided by molarity times S second. What is the overall order of the reaction? So what do we do when they give us information like these? I'll get my notes. Okay, so we're gonna do it together. I mean, you can think on it if you want to. Stop the video right here and do it on your own if you want to, but I'm gonna go ahead and think it through with you. So they give us these. Okay. And they want to know the overall order of the reaction. Remember that this is X plus Y. Okay? That's where it came from. What else do we know? We know that the rate equals a constant, which they give us, multiplying the concentration of reactant A to the X, multiplying the concentration of reactant B to the Y. So the constant, this constant, equals what? It's R divided by the concentration of A to the X multiplying the concentration of B to the Y. And this has to be 1 times, not times, divided by molarity divided by also the time, seconds. With these units, we should be able to see where X and Y are coming from. We know that the units of molarity, so the units for the rate are molarity divided by second. We know this because I gave you a PowerPoint a minute ago that told you those were the units. So what is going on here? There's an extra anything? We will see. Let's keep reasoning this through. We have these. What else do we know? We know that concentrations, okay, are given in molarity. So we have these, and we also know that concentration of B to the Y is also going to be a molarity. Molarity to the X and to the Y for each one of them. We know these, okay? So far, so good. Okay. Let's keep thinking a tiny bit more. So R was given to us, but for right now we don't need that. The value is not important. We have to focus on using these two to figure out what order X and Y this is. So what do we know? We are going to go from here to R has these units. M divided by S. Great. The concentration's units are M to the X multiplying M to the Y. This right here is the same as this. M divided by S, M, X plus Y. Okay, this is all algebra, so I'm just moving things around. Let me clear a tiny bit, and you can review these if you need to. I'm gonna clear this part right here. I'm just gonna leave these right here. Oops, I should not have. I'm gonna put it back. M divided by S. I hope everybody's following. So what do we have here? We have, I'm gonna write it again, okay? K equals MS divided by M X plus Y. So I can do this. Let me give you back the units for K. K was 34.51 M and S. So I need to get these units from this right here. How do I do that? How can I get these units from these? Okay, let's go this way. So if I multiply here by S, this is going to disappear. I can multiply this by S as well. So I'm going to be left with the one that I want at the top, and then I have an M here, and then I'm going to have M X plus Y multiplying S. I want a 1 here. How can I get a 1 here? Well, if this X plus Y equals 2, I'm going to have the following. Let me erase this right here. I'm going to have the following. I'm going to have M divided by M to the 2 times the S. So one of the M is going to be canceled, leaving the 1 M, and the S. And those are the units I wanted. So X plus Y needs to be 2. This is my answer right here. This is the overall order of that reaction. So this was backwards. You had to think backwards. And they may ask you questions like these. Not many, a few. I hope it makes sense. So let's look and see at the second problem. So number 2. Once again, if you want to try to do this on your own, go ahead and do that on your own. And then check to see if you are right. If not, just check to see how this is thought through. Number 2 says the following. The order of a chemical reaction with respect to one of its reactants is 3. If you double the concentration of that reactant, what happens to the rate? So let's see. What do we know? We know we have a concentration of a reactant. We don't know what it is, the reactant. But right now, we don't know. We know concentration are those brackets. We also know, according to the problem, that the order of a chemical reaction with respect to one of its reactants is 3. So this is a 3 right here. What else do we know? We know that now the concentration is going to be doubled. So 2 times the concentration. Everybody sees that? We're doubling the concentration. The order is still 3. So what happens to the rate? Well, we have 2 to the 3 multiplying the concentration. We don't know the concentration to the 3. So 8 multiplying concentration to the order 3. What happened here? The rate has increased by a factor of 8. Okay? So that's what you needed to do. It's a thinking process. And there's going to be a few of these kind of problems. Not many. So not many of this kind, but a few. Erase. Ask questions if this doesn't make sense to you. Okay, let's see if I can make this a tiny bit smaller. Maybe not. No. Okay, using experiments to determine the details of the rate equation. So how do we determine K? How do we determine the X and the Y, the order for concentration A, concentration B? Okay, so how do we do that? That's by experimentation. And you're not going to be doing those experiments. What you're going to learn to do is analyze the data that somebody else's experiments collected. So we're going to see tables of data and we're going to analyze them to find K, X, and Y. Sometimes the rate of the chemical reaction will be unaffected by the concentration of one of its reactants, as I showed you a minute ago. Let me see. I'm going to go back. Here you go. So one of the reactants may do this. You're increasing the reaction, the concentration, but there's no change in the rate. Okay? So sometimes that's going to happen. When that happens, the exponent of the rate equation for that reactant is 0. Take this into consideration, please. Now, let's see what kind of things we need to be able to do for this module. Page 466, example 14.2. A chemist runs an experiment designed to determine the rate equation for the following reaction. They give it to you. To do this, she runs the reaction 3 times and collects the information in the table below. Use this information to determine the rate equation for this reaction. So they're going to give you tables with all the data that's been collected from the experiment they perform. But you need to be able to find whatever they're asking. So the rate equation for this reaction is going to require you to find K, X, and Y. And how do we do this? Okay, I was trying to see if I could copy this to go on the whiteboard to explain what's going on, but I don't know how to. So I'm going to have to explain it here first. Let's look at this. You have trial 1, 2, and 3. You have the concentration of the first reactant. So this is A. Okay, it's going to give us the value of X. And here you have the second reactant, hydrogen. And this is going to give us the value of Y. And this right here is going to help us calculate those X's and Y's and then find the K. Let me write for a minute so we know what we're talking about. The reaction rate equation looks like this. K, concentration of reactant A, here is this 1, and this is to the X. And reactant B is the second reactant, which is going to be our hydrogen to the Y. So we need to find X, we have to find Y, and we have to find K. Let's go back. Okay. Let's look at the trials here. The first trial, both concentrations are the same. Here's the rate of the reaction, so how fast the concentration was changing over time. Great. What happened in trial 2? The concentration of reactant A did not change. The concentration of reactant B changed. How? Well, it doubled. Okay. Oops. Let me go back. If I touch it with a mouse, it moves. Here, the concentration doubled from 0.25 to 0.50. This increased by a double. What happened to the rate because you double the concentration of reactant B? If you divide this one by this one, you'll see that it doubled as well. The reaction rate doubling here between trial 1 and 2 is due to reactant 2 doubling as well, because the first one did not change at all. So any change in the reaction rate is due to this increase right here. What exponent makes a 2 become a 2? It's 1. Okay, so we know now oops, go back. Let me go back to the board. The x equals 1. And the way to think about it is the concentration doubled, the rate doubled as well. Okay, so how does it go from a 2 to a 2? What exponent makes this possible? X equals 1. That's the way to think about it. Okay, so let me erase these. We have the first one done. Let me go back to the example. Now, I'm sorry, this is not X, this is Y. Y equals 1. Remember that Y is for the hydrogen. Okay, so the change here was for the hydrogen. Let's look and see for the X's. The X's are related to the first concentration of the first reactant. Between trial 2 and 3, there is a doubling of reactant 1, but reactant 2 did not change. The rate changed, and it changes in the rate between trial 2 and trial 3 are due to the change in concentration for reactant A. This one had nothing to do with it. So this doubled, and if you divide this number by this number right here, you'll see that it also doubles. And once again, the exponent that allows that to happen is 1. X equals 1. And again is, how do you go from a double? It's 1. How do we calculate now? How do we calculate K? Well, you can use any trial to calculate A and stick with the numbers in the same trial. So let's see, I think the book uses trial 1, but you could use all the numbers in trial 2 or all the numbers in trial 3, and it would give you the same value. Let's check to see how this is done. Let me erase this so we have more room. So let's see. R equals X, concentration of the first, and we know that this is a 1. You don't have to put a 1. Okay? Anytime that you have an exponent 1, you leave it alone. And multiplying the concentration of the second one, second reactant. In trial 1, the rate is 0.0102, and the units are molarity divided by second. K is the unknown. The concentration in trial 1 for the first reactant is 0.25 molarity. And the concentration for the second reactant is also 0.25 molarity. Well, divide all of these by 0.25 molarity, divide by 0.25 molarity. You're doing the same thing here, okay? This is algebra. This now has disappeared, and you have the K by itself. So K equals 0.161 divided by molarity times second. So this is the constant. X was 1 and the Y was also 1, and those are the 3 things the problem was asking us to find. Remember that the units for K are going to be different for different reactions. So don't think that these are the only units you're going to encounter. They may vary. They could be molarity to the 2 or 1 per second. It all depends on the rate, on the exponents that you're using up here. Okay. So this one is solved. This one is solved. Let's do another one, and then we're going to do 3-4 of extra practice problems. I'm high grounds with the mouse. Okay, page 470, you have the second, let me see, I think I went too far. Page 469, example 14.3, reads like this. A chemist runs an experiment designed to determine the rate equation for the following reaction, and it's given to you. To do this, she runs the reaction 3 times, so there are 3 trials, and collects the information in the table below. Use this information to determine the rate equation for this reaction. Let's look at this. This is A, so this is gonna help us find X. Oy. If I touch a tiny bit the screen, it moves with the mouse. I'm sorry about that. This is B, so column B is going to find Y, and these are the instantaneous rates at different concentrations, different trials. So all of it together is going to help us find K. Let's study this in more detail. In trial 1, you start with this concentration and this rate. What happened in trial 2? The concentration of B did not change. Concentration of A changed. How? It doubled. Everybody sees that? It doubled. Any changes in the reaction rate right here are due to the changes in concentration of reactant A. So this is going to help us find X. Let's study how it changes. If you divide 0.076 by 0.019, you'll see that it quadruples. So let me go to the board. We're trying to find X now. Okay, so the concentration has doubled. Okay, while the rate, what happened to the rate? The rate has quadrupled, 2 and 4. I don't know how to put this in a nicer way, or how to explain this, but I'm explaining. I'm trying to do. We need to find exponents. What exponent allows us to do this? How do you go from a 2 to a 4? Well, if the exponent here is 2, you'll get your 4. So X equals 2. I hope this makes sense to you. The concentration doubled. Is this 2 right here? Let me do this again so we can think it through. So it doubled, but then an exponent allowed it to change to quadruple. So what exponent allows us to do that? X equals 2. 2 times 2 is 4. And that's where you found that 4. I hope it makes sense. Let's look at the next one. So now we want to find Y. We want to see changes in concentration of Y. When does that happen? Between trial 2 and trial 3, it doubled again. And what happened to this rate? What happened to the rate? The rate doubled as well. So basically, it went from a 2 to another 2. What X allows us, not X, this is Y we're looking for. What Y does that? If Y equals 1, this is true. This is true if Y equals 1. So now we found that X equals 2, Y equals 1. The next step is to find K. So this is our rate equation, and we just need to substitute everything by the information given in any of the trials. Just be consistent and stay with one of the trials. And let's see, he chose in the book, he chose again trial 1. So the rate for trial 1 is 0.019 molarity per second. K is what we're trying to find. Concentration for A is 0.5. Our X is 2. And then the concentration for B is 0.5 again, or 50. 50 is the same. And the Y is 1. Okay? So this right here, if we solve for K, is going to allow us to find K. So let's do that. Let's do the math here. K equals 0.019 molarity divided by second divided by 0.25 molarity to the 2. Remember that these two affects, this is the units as well. This is molarity, okay? And then this is 0.50, the molarity. And if you continue canceling things, you're going to find that you have 0.15, 1 divided by the molarity to the second times the second. So you see how the units here are different because our exponents were different. So be careful with that. The units of the rate constant vary. They depend on those exponents, the order for each one of those, reactants. And they're asking us to write the rate equation. So we have one more step. We need to put it all nice and pretty. The rate is going to be the K we just found, 0.15, 1 divided by molarity to the second power, S, and that's multiplying whatever concentration. So at any time when the concentrations change, you can use this to find the rate. And O2 multiplying Cl2 and the 1 you don't need to put. So this right here allows us to find the rate, knowing the concentrations of the two reactants at different times in point. Okay. Now the second section for this example reads as follows: in order to determine the rate equation for the following equation, and I think I have a copy of these. Let me see. Yeah, here you go. Second section. So they give us the reaction right here. A chemist performs a rate study and gets the results below. So we have trials 1 to 3. What is the rate equation for this reaction? Once again, we're going to have to find X, Y, and K, and then put it all together. Well, let's study. You started with this concentration, with this rate. What happened here? When you went to trial 2, you left concentration B alone, but you changed the concentration of A. So we can find X by studying the difference between trial 1 and trial 2. What happened here? It doubled. Okay? And what happened here? Well, it looks to me like it also doubled. And what does it mean? If it doubles and it doubles, it means that the exponent X had to be 1. So we know that X is 1. Let's study column number 2. This 1, nothing changed. But between trial number 2 and 3, the concentration changed. It doubled. Any variations here are due to this change in concentration for B. Maybe, or maybe not. Because look here, it also changed. Between 2 and 3, it changed too. So we cannot determine by studying 2 and 3 who was in charge of changing the rate here. We need, whoops, it does happen all the time. Let's go back. Okay, we need to find trials in which the rate changes because the concentration of B changed. Only B changed. A cannot change. So the concentration changes between trial 1 and 2, and the concentration between trial 1, try this again. The concentration changes between trial 1 and 3 went from 0.10 to 0.20, so it doubled. Between trial 1 and 3, the concentration of A did not change. So we cannot pick 2 and 3 this time. We need to pick 1 and 3. Okay, great. So that doubled. What happened between the rates? Trial 1 and trial 3. Nothing changed. We learned that if the rate did not change when you change the concentration, the exponent was 0. So far so good? So let me write this down. We have R equals, okay, which we have not found yet, the concentration of, and our exponent, x was 1. Remember, we don't write it. And the other one is 0, which makes this 1. Anything exponent 0 is 1. So basically, it's this. From here, we can find K. Pick up any of the trials. And once again, in the book, he picked trial number 1. So the rate there was 0.0010. And then the K we're trying to find, and the concentration for this compound is 0.10 molarity. So divide everything by 0.10, and you're going to find K. And K equals 0.010. The molarity is cancelled, so you're left with just seconds, 1 per second. Now, are we done? No, because they asked us for the equation, not just the values, but the equation. So the equation is going to be R equals, we found this, and multiplying any concentration that they give us. The rate can be calculated by using this equation. Given a concentration, knowing the constant, we can find the rate of that reaction for that concentration. So that is done. Now, I would like for you to try extra practice problems number 3 and 4 on page 582. I'll give you the values, and if you get it, move on. This is a video, and if you don't get it, then I'll break it down into steps. Let's start with number 3. So for number 3, our extra practice problems, let's see what they're asking. They're asking for the equation. So if you got this, I'm copying it from my notes. You're done. So basically, x was 2, y was 1, and then the k was this amount. And I don't have the tile information. You're gonna have to have it in front of you while I try to explain this to you. So make sure that you have page 582 in front of you. We're doing number 3. It says a chemist does a reaction rate analysis on the following reaction. They give you the reaction so you know who is A and who is B. They collect data, trial 1, 2, and 3, and then what do we need to do? So we have that NO is going to allow us to find X, and the chlorine is going to allow us to find Y. And we need to check how the rates change depending on whose concentration is changing. So let's check for X. There is a change in concentration between trial 1 and 2 for nitrogen monoxide. How? It goes from 0.050 to 0.100. This has doubled. Okay. So what happened to the reaction rate? between trial, this is trial 1 and 2. We need to check the rates and see how that has changed. How did it change? Well, 0.113 to 0.452, it quadrupled. So it became a 4. What exponent allows us to do that? A 2. 2 to the 2 will become this quadruple 4. So that's why we have an x that equals 2 right here. So that one is done. To find y, we need to check the trials and see where the concentration change, making the rate change as well, but with no change in reactant A. When does that happen? Well, we have trial 2 and trial 3. It went from 0.050 to 0.100. Okay? So this is trial 2 and trial 3. So we need to concentrate on what happened here. Here it happens that it doubled. I should put a y. Okay, I'm sorry. I need to be consistent here. So it doubled, and we need to find how this doubling affected the rate. So let's look at the rates for 2 and 3. If you look at the rates, you will see that it also doubled. So y needs to be 1 for this to be true, for this equality to be true, okay? For this to be related to one another. For one to double and the other also doubles, the exponent that makes that possible is a 1. So that is done. Okay. Now, to be able to calculate k, the only thing you need to do is plug everything in from one trial, pick trial 1 or trial 2 or trial 3, but stay in the same line with all the information, put it in the equation with the right concentrations for A and for B with the exponents we just gave them. So this is a 2 and a 1, and you can find k from here, which is this one right here. I hope this makes sense. Now erase these. Number 4, let me give you the information for number 4. So once again, you get it right, move on. You don't get it right, then just check to see how I'm thinking through the problem. This is just reading the information that's given on those tables. So let's see what 4 is asking. 4 is asking again for the equation. So this is what mine looks like. This is your K, and then the concentrations for each one of those reactants, and it looks like the order for each one of them is 1. So x equals 1, y equals 1, that's why we don't write them, and this is our K, this equals our K. So where did we get that information from? Okay, let me erase these. Go back to the table. Once again, it's on page 482. I'm not going to copy the whole table here, but I'm going to talk about the trials. So let's look at the trials. This is A and this is B. So A is X and B is Y. So if you look at column for the first reactant, you will see that the concentration stays the same between trial 1 and trial 3. It's the same, exactly the same. Nothing changes. But the concentration changes between trial 1 and 2. What happens with the concentration of reactant B between trial 1 and 2? It stays the same. Great. So the reaction rate has changed because you changed the concentration of the first reactant between trial 1 and 2. What happened here? Between trial 1 and 2, what happened to the concentration? It doubled because it went from 0.1 to 0.2. Need to find what x will give us the change in rate. So between 1 and 2, it also doubles. And for this to be true, x needs to be 1. The 1 we don't write down, just leave it alone. So that is done. That one is done. Now, to find this y right here, we needed to study, again, changes in the rate because of changes of concentration, but in column 2 for the reactant B, for this reactant right here. Between trial 1 and 2, there is no change in that reactant's concentration, but there's a change between 2 and 3. Oh, great. But there's also a change between 2 and 3 for reactant A. So we cannot use trials 2 and 3 because both of them change concentrations. So we don't know who is responsible for, both of them are responsible for the change in the rate. But there's also a change between, for reactant B, there's also a change between trial 1 and 3. And if you look at A, between 1 and 3, there is no change. So we can use trials 1 and 3 and say any change in the rate is due to the change in concentration of reactant B. What happened to the concentrations between 1 and 3? Okay, I double again. So what happens to the rate between 1 and 3? It double as well. So for that to be true, y needed to be 1, which is what we found right here. And now we have the y done. To find k, just plug it in, pick up a trial, put the rate for that trial in here, the concentration of A, remember this is A to the 1, and the concentration of B also to the 1. So pick up one of the trials, it doesn't matter which one, just stick in the same trial for all the information. And that allows you to find k, which is this number right here, this value. And it finishes extra practice problem number 4. Page 472. The rate order. We talked a tiny bit about the rate order a minute ago, but it's important enough to give it a second try here. The exponents x and y in the rate equation are referred to as the order of the chemical reaction. Chemists often communicate the rate equation in terms of this reaction order. For example 14.4 in your textbook, page 473. Says a chemist does a rate analysis and they give you the reaction. The experiment reveals that this reaction is first order with respect to each of its reactants. What is the rate equation and overall order for the reaction? Okay, so remember what that is. R equals first reactant to the X, okay, constant, and the second concentration for reactant B to the Y. What did they say to us? They said that the first reactant, according to the reaction they give us, is hydrochloric acid. And they tell us that is in first order with respect to each of the reactants. First order means 1. So this is 1. It means that X equals 1, and the other one, Y, is also 1. So we have these. Who is B? The sodium hydroxide. So this is a base acid reaction. So this is the rate equation that they were requiring us to write down. We don't have any more information to put K or the rate here or anything else, but being first order means 1. And now they want to know what's the overall order. The overall order of the reaction is y plus x or x plus y, doesn't matter. This is 2. 1 plus 1 equals 2. A chemist would say, oh, this reaction is a reaction of the second order. That's what they would say. They talk like this. They are fun that way. And that's all it is. It's just add them up. This ends this module. We've finished. the first half of this module. Sorry, I got excited here. This finished the first half of the module. Read your textbook for this week. Add to your notes if you need to. Work all the examples. There's one experiment to do this week. And study for your test, and take your test, and also study for your quiz. So if you have questions during the week, email me, and then see each other on Friday when we have our Zoom meeting. I hope you all have a good week.